Hi, this is lesson 26 in the use of JASP for understanding statistics. And today we're talking about the one-factor analysis of variance. I want to pull something from the JASP library today. And so we're going to go to our three lines on the left-hand side, go down to Find Data Library, and go over to ANOVA. Over in ANOVA, I want you to go on down, and we're going to find this pain threshold data. Load that up. This is illustrating analysis for doing this in Bayesian, which I'm not going to do right now. So let's just get rid of what comes up. And we'll start from scratch. And this is a analysis that looks at data that relates hair color to pain tolerance. So individuals are given some kind of pain task. Doesn't specify what that pain task is, but a pain task could be, for example, how long you're able to hold your hand in ice water. And we're looking at that as a function of their hair color. And we have four groups. There's individuals, participants that have light blonde hair, dark blonde hair, light brunette hair, and dark brunette hair. And then we have their pain tolerance values given. So they're divided up into groups. That's going to be our independent variable. Pain tolerance is going to be the dependent variable. It's a scaled variable. It's being treated as continuous. And an ANOVA, a one-factor ANOVA, is done when you have three or more groups and you want to compare them, their responses, with respect to a continuous dependent variable. So perfect. So go over to classical ANOVA. And under classical ANOVA, the grouping variable, which could have been called groups or could have been called conditions, but descriptively they called it hair color. We're going to take hair color and move it in as our fixed factor. That fixed factor should be recognized as your place where you put your independent variables that define specific groups. So you can think, it's an oversimplification, but you can think of that notion of fixed factor as fixed to specific groups. And we just have one factor for this ANOVA. So one variable goes in there and we're done. It has space for more, which is the reason why it's called fixed factors. Pain tolerance goes as the dependent variable, and up comes the analysis. It does the F-test, and basically it is showing, this is a source table. The source table is showing, I don't like that label cases. I usually, on my own source tables, in APA format, would put source, the source of your variance. But they put it as cases, so that's just a quirk of this program. Hair color, in most textbooks, you would find that as between treatments or between groups, either between treatments or between groups, but they're actually saying which variable defines the groups and calling it hair colors. There's groups of people who differ by hair color. There's four of those groups, and 4 minus 1 gives you the 3 degrees of freedom. Then for one-factor analysis of variance at the introductory level, you usually see the term within groups, where they have put residuals. So residuals, it's what's left over after you account for variability due to variance between groups. So the residuals is the same thing as the within group variance. You take this mean squared for the between groups divided by the mean squared for the within groups. It's 453 divided by 67 roughly. You get the F value of 6.791. You look up a critical value for 3 and 15 degrees of freedom, and it's probably going to be somewhere in the 3 or 4 range. This F exceeds that, and hence it gives you a p-value of 0.004. It is less than 0.05, so if you set alpha to 0.05, it's less than that, saying that your probability of a type 1 error is even less than 0.05, that it's about 0.004, which is very low, so we would call that a statistically significant result. To interpret this, by the way, the F table does not include a line for totals, which most other programs and intro textbooks do. So the total would just be the sum, just add the two sums of squares together, add the degrees of freedom together. So the total degrees of freedom would be 18. That's not shown here. It's not necessary, and so they don't do anything beyond what's necessary. We need to see the descriptive statistics because we do this F test in service of finding out if there are significant differences between these means. Since we rejected the null hypothesis with this analysis of variance, we are basically saying that at least one of these means is different from another. And so what that would point to is that you would assume that the largest, at least the largest mean of 59.2 for the light blonde hair is significantly different than the dark brunette, which is 37.4, the lowest value. But you really don't know what exactly is significant here, so you have to do further tests. There's two types of tests that you can do. One's called a priori test, which has its own little complications where we might even ignore the F table up here if we were going that direction. The most usual way of discerning these is to do a post hoc test. So a post hoc test means after the fact, almost on an exploratory basis, and that differs from a priori, which is basically you had a strong theoretical expectation, and so you want to allow for more statistical power in examining that theoretical expectation. I'll come back probably in another video to talk about that more later. Right now we'll focus on the post hoc test, so that means that we'll pass up contrast. We could do our assumptions check and look at the homogeneity test. And the homogeneity test basically is asking, are there significant differences between the standard deviations of these groups? Does one group have a lot more variance than another group? It comes up non-significant. That's what we want, because a significant test here would indicate that there are big differences, big significant differences between the standard deviations, one having a lot more variability than another. That would violate the assumptions, and we would want to then do corrections for those. And there's various corrections to be done in here. Oh, right here. So then you could click on saying, oh, okay, I want to do the Welch correction. And here the Welch correction basically comes up with the same inference. It's still significant. Differed a little bit because there's a little bit of a difference in the standard deviations. But since this was not significant, we didn't even really need to look at that. So I'm going to take that back out. We tested that, so I'm not worried about it anymore. I'm going to take that back out. And we'll just forget about our homogeneity of variance test. Okay. Post hoc test. So we're going to go over to post hoc test, and we're going to take our grouping variable, which is called hair color, and we're going to put it in here. And what it does is it starts doing what are called pairwise comparisons. It compares each group against the other group. It compares the dark blonde against the dark brunette, the dark blonde against the light blonde, the dark blonde against the light brunette. Each time given a mean difference. So those mean differences would be the same thing as going, 51.2 minus 37.4 gives you the 13.8, and it shows that's not quite significant because that value is a little bit over 0.05, and over 0.05 means my probability of a type 1 error is too large for me to reject the null hypothesis. So there's basically with 4 groups, there's 6 possible comparisons. You have all 6 laid out here. All 6 possible comparisons are then laid out. And you can click this button over here under display comparisons, and it's helps you see that there's 2 of these that are significant, one less than 0.05 and the other one less than 0.01. So the dark blonde brunette versus the light blonde is your biggest difference. That's your biggest difference of 21.8. What I really like for interpreting these is what's called is the letter-based grouping table. So it's basically showing that if you took and each group as lined up over here with their means, you could actually do subscripting of the means where you'd put an AB next to this mean of 51, an A here, a B here, and an A here. And the interpretation is shown here. If 2 or more means share the same grouping symbol, then we cannot show them to be different, but we can also not show them to be the same. So it's basically saying you can't prove that they're not different. You can't accept the null hypothesis. But if they're the same, so they're not necessarily the same, and they're not necessarily different. It's a convoluted way of saying it. I never write it quite like that. I would just say means that share a common subscript are not statistically significantly different from one another is the phrase that I use. And so what's that saying is that if they do have different subscripts, so here you have a B for light blonde, and you only have an A for the dark brunette and the light brunette, then I know that light blonde is significantly different than both dark brunette and light brunette, right? So the light blonde mean of 59.2 is significantly higher than that mean of 37.4 and is significantly higher than the mean of 42.5. That's also the same information over here, but this makes it easy to see once you get used to tracing it that way. You can also look at descriptive plots. Put hair color in on the horizontal axis. You can ask for a display of error bars. And originally it comes up not looking all that great. The words are all running over each other. Take and your cursor on this little corner, stretch it out, let go, let it readjust, and then it comes out with a nice plot. And here it becomes easier to see that the light blonde group right here is significantly different than these 2 groups over here. There's also bar plots, which basically are another way of showing the same thing. You can show the 95% confidence errors, or you can do the standard errors is another way of seeing where the differences are. Standard errors are smaller. And so here, if the standard errors aren't overlapping, then it becomes pretty obvious that the light blonde, since its standard errors don't overlap with the standard errors here or here, that this one is significantly different than these 2 groups. Finally, there are the rain cloud plots. Again, you can stretch this out, let it snap into place. And here it's actually showing the data points. It's giving you a box and whiskers plot so that you can kind of see where the medians are. It gives you a view of what the projected distribution is. It's not the real distribution, but what it's doing is it's basically projecting that if you had more data when the data points are closer together, then that's more of a peak to the normal distribution. And if the data are all kind of equally spread out, sort of like these purple ones are, then there's less of a peak and it's just, a flatter distribution. What you're looking for is, if you have significant differences, there should be noticeable differences in the distributions. You'll notice that the green and the purple distribution overlap a whole lot, indicating that there's no significant difference between the dark blonde and the light blonde. And but it does look like these two groups are different than these two groups, but that's not actually what we found. We didn't have enough statistical power to say that. Now, there is another analysis, that a priori analysis that I mentioned, which could give us more statistical power for saying that. But all we can say, based upon the analysis that we did, and if we honestly went in with no expectations, no strong expectations theoretically about how hair color would be related to pain tolerances, then what we should do is this analysis, because this analysis is designed, that Tukey's post hoc test is designed to correct for any exploratory type 1 error inflation. That is, it's reducing the likelihood that we're going to make a false positive. Type 1 errors are a false positive. It's reducing that for us. That's what we want for it to let us do. And so all you can do is assume that this one is significantly different from these two. Again, not based upon the figures, but you should trust the post hoc tests that are shown here where the significant differences lie. This one is different than this one. This one is different than this one. This one is different than this one at 0.037. This one is different than this one at 0.004. Okay, that's a one-factor analysis of variance with a Tukey's post hoc test. I will note, one thing that I kind of flew by is that there's a whole lot of post hoc tests. And that's for another day, another discussion as to why you'd use one for another. But there's a whole lot of post hoc tests that have been developed, ones that are that have been developed and not even listed here. And the Tukey's, though, is my go-to, and it is the most commonly used and commonly reported. So I hope that lesson helps. We'll talk to you later.